Hi, and today we're going to talk about exponential growth and decay. Exponential functions are functions that have a variable, x, in the exponent. Here is the standard form for an exponential function. Y is equal to a times b to the x. A is the starting value, b is the growth or decay factor. So if b is greater than 1, it's going to be growth, which means it gets bigger. But if b is between 0 and 1, it means that we're only using part of 1, which means it'll actually get smaller. Like 7 times 0.5 is 3.5. Okay, so without graphing, we're just going to determine whether or not this is growth or decay. So in this case, what we need to look at is this number right here. And since this number is between 0 and 1, that is going to mean decay. Now, we need to figure out the percent increase or decrease. Now, you might remember that if we were growing, it was greater than 1. And if we were decaying, it was going to be less than 1. So what we are doing is we are finding the distance from where we are to the level that we have. So from 1 to this. So I would do 1 minus 0.12. And that gets us 0.88, which means it is a decrease of 88%. There we are. Now let's try this one. If you look right here, this is greater than 1, so it is growth. Now let's try to figure out our value. In this case, the distance from 1.74 to 1 ends up being 0.74. Which means 74%. Now let's try this one. Oh, this is way more than 1, which means it is definitely growth. So I would do 3.4 minus 1, that is 2.4, or 240%. Here's our last one, 14 over 10. Let's see. I'm going to rewrite that as 1.4. The decimal version, subtract 1, 0.4 or 40%. And that is growth. All right. A new car sells for $18,000 and it depreciates by 25% each year. Write a function that models the value of the car, and then what we're going to do is find the value of the car after 4 years. So in this case, this is our initial value, and then because we are depreciating, we are doing 1 minus 0.25, which is 0.75. That means 75%. And then we want the value after 4 years because this would be our formula. What I'm going to do is I'm going to put this in a calculator and I'm going to multiply that by 0.75 to the 4th power because my x value is 4. So after 4 years, your car is now valued at, if you are only keeping 75% each year, $5,695.31. All right, an abandoned house has a mouse problem of 22. It is increasing at a rate of 5% per month. So what we're going to do is write a function that models the population. Let's start with that. Our initial value is 22 times, in this case, 5% increase means 1.05. That's 5% more than 1 to the x power. And that's going to equal however many we have now. So in this case, we know it's actually going to equal 50. So what I would do is I would place this into a calculator and I would go and look at the table. And what I would see is that right around between 16 and 17 months is when it hits 50 because it's only a little over 50 at 17 months. So I'm going to say 16 to 17 months. All right, now we're going to write an exponential function. Y equals ab to the x for a graph that includes these points. So let's see. y equals ab to the x. Well, the first thing I know is that this gives me an x and a y value. So in this case, my y value is 2 equals a times b to the 0. Well, that's important because b to the 0 is 1, which really means 2 equals a. Now that I know a is 2, I'm going to plug that into my second equation. So, let's see. 6 equals 2 times b to the first power. In other words, 6 equals 2b, so I can just divide both sides by 2. That means b equals 3, meaning our final equation is 2b to the x. Sorry. Y equals 2 times 3 to the x. All right, so let's look at this one. Now, there are a few ways that we can do this one, and I'm just going to show you one right here on this video. The first way we can do this is I'm just going to write both equations. So, 4 equals a times b squared, and 16 equals a b cubed. Now, the reason why this matters is I could rewrite 16 equals ab cubed to be 16 equals ab squared times b, because b cubed is b squared times b. The reason why that matters is ab squared could be rewritten as 16 equals, I'm going to substitute 4 for ab squared, b, divide both sides by 4, b equals 4. Now that I know that, I plug that into one of my two equations. So I'm going to go 4 equals a times 16, divide both sides by 16. 4/16 is 1/4. So y equals 1/4 of 4 to the x. All right. For each annual rate of change, find the corresponding growth or decay factor. So since this is an increase, we do 1 plus 0.35 or 1.35. Let's try this one. So since this one is a decrease, we do 1 minus 0.47 or 0.53. Exponential functions are actually used to represent many different real-life situations, and well, here are a few. We're going to start with the Richter scale. Now, for those of you that don't know, Richter scale is about earthquakes. The energy released by an earthquake can be represented by the equation E times 30 to the x. X is the magnitude of the earthquake on the Richter scale. Now, you might be asking, what is E? And I want to point out this is the capital letter E. But in this case, E represents some amount of energy that was present in the earth originally. In other words, kind of the base level. So if you're into like recording music, kind of your room tone, what you have before you do anything, your white balance. So E is kind of like, this is how much energy the earth has just being the earth. So it's not important though for this application, and here's why. To compare magnitudes, we use this formula. E times 30 to the x, x1 being the first earthquake, over E times 30 to the x2. Now here's the reason why E didn't really matter. We have E as a common factor on top and bottom, meaning they cancel out. So let's try this one. 1995, an earthquake in Mexico registered an 8.0 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington State. Compare the amounts of energy in the two earthquakes. So what I would do here is I would say 30 to the 8th power over 30 to the 6.8 power. So at that point, what we have to remember is our rules about exponents. In this case, remember, if I'm raising x to the 5th over x cubed, we can subtract them. So this really becomes 30 to the 8 minus 6.8. Let's rewrite that. 30 to the 8 minus 6.8, which means 30 to the 1.2, which ends up getting you 59.23, meaning the earthquake in Mexico is 59.23 times bigger than the earthquake in Washington. Now we're going to talk about half-lives. Half-life is a method of figuring out how old certain substances are. When we know how quickly a substance decays, we can use that information to find out how long it's been sitting around. In this case, we use this formula. A times 1/2 to the T over K, where A is the initial amount, T is the time, and K is the half-life. Please note, time and half-life have to be the same measure of time. So if I'm saying minutes, it needs to be minutes. Hours, hours, days, days, months, months, years, years. So, technetium-99m has a half-life of 6 hours. Find the amount of technetium-99 that remains from a 50 milligram supply after 25 hours. So, in this case, what we would do is we would say 50 times 1/2 to the, how many hours were there? 25 over the half-life of 6. So, 50 times 1/2 to the 25 over 6. And you end up getting 2.78 milligrams being left over. Here's our next one. Arsenic 74 is used to locate brain tumors. It has a half-life of 17.5 days. So now we need to write an exponential decay function for a 90 milligram sample. We're going to use the function to find out the amount that's remaining after 6 days. So we start out with our initial value of 90 times 1/2 of there were, in this case, 6 days out of the 17.5 to get a full half-life, meaning we will not have a full half taken out. So 90 times 0.5 to the 6 over 17.5. There will still be 70.96 milligrams remaining. Now we're going to talk about compound interest. When you invest money in an investment account or even just a bank, it collects interest. That means that the bank will give you a small amount of money just for letting the money sit in their bank. It's because they use your money and they kind of let other people borrow it. So they're not really just letting it be there for the pleasure of its company. But interest is compounded or calculated a certain number of times per year. And that formula is this. Y equals A times 1 plus R over N times N to the NT. So A is the initial amount, R is the interest rate, N is the number of times compounded, and T is time. So in this case, I invest $100 at an annual interest rate of 4%. So times 1 plus 0.4. Now, it is compounded quarterly. Quarterly means 4 times a year. So over 4 times 4 to the, how much will you have in 25 years? So this is our equation. So all we have to do is put this into a calculator. 100 times 1 plus 0.4 over 4 to the 4 times 25. I realize I made a mistake. This is not 0.4, it's 0.04. Let's try this one again. 100 plus 0.04 divided by 4 to the 4 times 25. And you will find that over the course of 25 years, you have earned $270.48. Continuously compounded interest. Continuously compounded interest is what it sounds like. There are not a certain number of times that it's calculated. It's actually done at all times. So like if I put $1 billion in a savings account with 5% interest annually, it would be like, well, for 5 minutes you had it in, so it's like you were earning interest off of that 5 minutes. It's done all the time. So here's the formula for that situation. A equals P times E to the RT. P is the initial amount, R is the interest rate, T is time. Please notice E right here. That is an actual number. That is what's known as a natural number, and if you put it into your calculator, you will find that it's worth about 2.718. But it's irrational like pi. So you invest $1,050 at an annual interest rate of 5.5% compounded continuously. So 1,050 times e to the 0.055 times how much would you have after 10 years? So all we have to do is plug this in. 1,050 times e to the 0.055 times 10. And you would discover that you had, after 10 years, $1,819 and we're going to say 2 cents. It's 91.5, but 92 cents. All right, let's try this last one. A student wants to save $8,000 for college. Now, notice $8,000 is not how much we put in the bank. We're going to find that out. How much should be put into the bank if the account earns 5.2% annual interest compounded continuously? So that means $8,000 is going to equal whatever we're looking for times e to the 0.052 times, in this case, 5. So I do not know what e to the 0.052 times 5 is, but I do know that whatever it is, it's being multiplied by e to get 8,000. So I divide both sides by e to the 0.052 to the 5th power on both sides. Over here, it cancels things out, giving us x. On the other side, we get 8,000 divided by e to the 0.052 times 5. You end up having to initially invest $6,168.41, give or take. And that's it. If you would please like or subscribe. I will have another video up very soon over logarithms. Have a good day, and thank you very much.